repeatedly you got some problem. Because this solution, if you look carefully, it's not stable. Why? Cosine t, the first thing, cosine t is okay, because it is just oscillating. But t cosine t is no good, because it's growing. Alright? In the system, in a dynamic system, the second, the t cosine t means you have an unstable term in this. So, in this four terms, C1 cosine t plus C3 sine t, we don't worry about it. But C2 t cosine t and C4 t sine t, we gotta worry about it. Hopefully C2 equal to 0, and C2 equal to 0, and C4 equal to 0, then we solve the problem. And life is not that easy like this. So there's some system like this. Now, you might ask, do we have a system with a force power of this? Any system with force power of this? Well, the answer is yes. All right. Now let's look at multiple roots. All right. I'm going to talk about all this, and this happened in the dynamic system too. So this is why we spent some time to redo it here. Even the Dr. Wang already taught you some of the math, so I'm not going to focus on math. I'm focusing on the physics. So we have the roots. Gamma 4 equal to -1. Then we have 4 roots. Now how can we write this? -1 equal to e sine I pi plus 2 n pi. Can we do this? How do we know we can do this? All right, that's the way you solve it. How do we solve the 4 roots of gamma 4? The gamma 4 equal to -1. Alright, we know that the -1 we can write in terms of e to what I pi plus 2n pi. Okay, because that's equal to cosine pi plus 2n pi plus I sine pi plus 2n pi, right? Is that true? That's true, right? So, this exponential is a good function to be used, because it will always give you some nice, neat, simple, just one exponential. But don't forget that this exponential, there's an infinitive series behind that exponential function. Right? So keep thinking about that. This is just very convenient to write it, but it doesn't mean that its solution is exact solution. That's the approximate solutions. Okay. So if you write this, then the first power of that you can write in terms of divided by 4. Then you got a 1, 2, 3, 4. 1, 2, 3, 4 function for that. That's the 4 solutions for this gamma 1, gamma 2, and gamma 3, and gamma 4. And so that is the solution for the gamma 1, gamma 2, gamma 3, and gamma 4, that's gamma 1 is equal to 1 plus I over square root 2, and gamma 2 is minus 1 plus I square root of 2, and then if I ask you that this system is stable or not, can you tell me? Just look at these four roots. So it's stable or unstable? Unstable. Why? Because there's a positive three roots. Exactly right. Yeah, so you learn very quickly. So look at these four roots. You will be able to tell you if the system is stable or is unstable. All right? That's important because that's control. If you see an unstable dynamic system, then you are asked to design a controller to make the unstable system become stable. That's much harder than originally your system is stable. All right. So this unstable system will give you that four different solutions. All right, because you have the negative real roots, you have positive real roots. The negative real roots, we really don't worry about that, but the positive real roots, that's the one we have to worry about. Now, these roots, later on I will show you, this root nothing but just eigenvalue of a matrix. And that matrix represents the system. Like this, see? Now, the negative real roots, we don't worry about that because it will decay to 0. The positive real root is going to grow. See? 0 and only about 6 seconds grow to minus 30. And this one, the same thing, going to grow. All right. Well, this is the coefficient. The coefficient there is you have to be careful this plot because there's some negative sign involved in there. But this just shows you doesn't matter grow in the negative side or grow in the positive side. It's growing. So that's we call the unstable term here. There's two unstable terms. There's two stable terms. Doesn't matter. The only way this system becomes stable is that if your C3 equal to 0 and C4 equal to 0. Now, let me ask you, how you compute C1, C2, C3, C4? What? The C1, C2, C3, C4. How you know C1, C2, C3, C4? So homogeneous solutions. To solve coefficients of a homogeneous solutions, how do you solve it? You have to know the initial conditions. If you all initial conditions are 0, this is supposed to all 0. You have to solve. So maybe you can say, I can find an initial solution such that C3 and C4 are 0. Yes, good luck to you. That's good. If you don't, then you need to design a controller, hopefully to take care of these two terms. All right. So that's two terms. It is very unstable. So at this moment, to this point, to this end, we learn the damping, the relationship between the damping and your roots. The relationship between the oscillation of the system with the roots. So I already told you that the real power eigenvalue, real power roots that's related to the damping. The imaginary part of the roots that related to your oscillations, your frequencies. That's just like a spring. Okay, now, if I become a negative, say, okay, now if gamma 4 equal to 1 is not equal to minus 1, then you still have 4 roots. Now gamma 1 equal 1, then gamma 2 is I, gamma 3 is minus I, minus 1, gamma 4 is minus I. All right, and this is the roots, 4 roots you got. Okay. Now I'm asking, is it stable and stable? This is stable and stable. This is still unstable. Because you have real roots which is positive. So the solution is like this. But here we have only one term. That's the ET. That term is unstable. In the last slides, we have 2 unstable terms. This slide, we have 1 unstable terms. So when you design a controller, or when you look at a system, then you better pray and say, hey, don't give me a real part of roots which are positive. Because you know that as soon as